Okay, so thank you to all of you, first of all, for joining us on this occasion. It's really nice to see so many people here on the 10th anniversary of ICTS. It's been about 5 years since I came here, and 5 years ago, I remember we had we were just doing the ground laying ceremony, and this was just wilderness, and so the change in the intervening 5 years has been enormous, and I hope you'll keep coming back and keep growing this way. Thank you also to Rajesh for putting me in this computer science session. Before I wanted to be a physicist, I wanted to be a computer scientist, and so I'm glad that at least for today morning I can pretend to be one. I'm going to talk about information, but from a very different perspective. I'm going to talk about information from the perspective of black holes. So let me just start by giving you some background. It was realized soon after general relativity was discovered, pretty soon after 10 or 15, 20 years, that if you had a star that was massive enough, the star would collapse under its own gravity and it would form a black hole. And the reason black holes are called black is because classically, these black holes don't emit anything. They only eat up more stuff. And the precise version of that statement is that the area of black holes never decreases. So these are things that were understood well till about the 1970s, when Hawking pointed out that in fact you needed to put caveats to the statement. And in particular, what Hawking showed was that if you added quantum effects to black holes, then these quantum effects would mean that black holes were no longer purely black, but rather that they emitted thermal radiation with a temperature that was proportional to some fundamental constants and inversely proportional to the mass of the black hole. Now, if you think about it, because this radiation causes the black hole to lose energy, it means that this cycle you had of a star forming a black hole, eventually, if you wait long enough through Hawking radiation, gets completed by the black hole evaporating away entirely into some gas of photons and gravitons and some other particles, limits. Now, the surprising aspect of Hawking's calculation was that Hawking found that the radiation that was emitted by the black hole, to a very good approximation, didn't depend on what constituted the black hole in detail. It only depended on a few macroscopic parameters like the mass of the black hole. Now, if you think about this a little bit more, you will see that this immediately leads to a paradox. And the reason it leads to a paradox is that you could imagine the following kind of process, where you started with one star that was made of one kind of material, and then you allowed it to form a black hole, and then allowed it to radiate through Hawking radiation, and you would get radiation. And then you could take another star, which was of the same mass, but was made of a completely different kind of material, and then that would form a black hole, and that would give you the same kind of radiation. Now, we know that in physics, these kinds of processes are not allowed. In particular, this is in contradiction with the unitarity of quantum mechanics that tells you that time evolution has to be reversible. So you can't have these situations where you have two distinct initial states leading to the final state. So this is what, in its crudest form, is called the information paradox. Now, the information paradox is really a central issue in putting together quantum mechanics and gravity, because it suggests that maybe you can't have a theory of quantum gravity. It suggests that you do some calculation using some robust properties of gravity, and then that turns out to be in contradiction with some other very robust property of quantum mechanics. But a common criticism of the paradox, and in fact of people working on the paradox, was that the paradox is not very precise. It's not very precise because maybe there are small corrections to Hawking's computation, and these particles that are emitted, maybe they have small correlations. The particle here has some tiny correlation with the particle that went on the other side, and maybe these small correlations can between all of them preserve all the information that went into the black hole in the first place. And we didn't really have a good way of computing all of these correlations to the accuracy required, so people believe that maybe there wasn't really a paradox. There wasn't really a precise enough frame, the paradox. So what I want to describe to you today in this talk is that in the past few years, there have been several new ideas on this subject. And what these ideas have allowed us to do is that they've allowed us to make the information paradox precise and frame it in settings where we can actually do contradictions, where we can actually do calculations and see the presence of these paradoxes in a much sharper setting. And some of these most interesting versions, as I'll describe, appear in a setting called holography. And what's nicest about these paradoxes is that thinking about them is not only an exercise in itself, but rather that it tells us about novel aspects of quantum gravity. And as I'll try and describe to you. Okay, So let me just give you a one-slide summary of holography. I won't use too many details. So holography is an idea that was proposed by Maldacena in 1997. And Maldacena pointed out that sometimes if you looked at gravitational interactions of these blue particles in a certain kind of space called anti-de Sitter space, then these gravitational interactions could be modeled exactly by some unitary non-gravitational interactions that lived on the boundary of the space. And that's why this idea is called holography, because these non-gravitational interactions live at the boundary of the space that hosts the gravitational interactions. Now you see that this allows you to translate the information paradox to a slightly different question, because you have these unitary, this unitary theory that lives on a boundary. The question then really is, is holography complete? Does holography give you a description of the formation and evaporation of black holes in detail? And if it does, then you know that in this tussle between gravity and quantum mechanics wins. You know how it wins. This dictionary, you use this to understand what happens in the bulk. So you see that holography already allows you to translate the problem, the original problem of information loss. In fact, you can simplify the problem a little bit more, and I can ask the following kind of problem. You see, you could think of a process of this kind. By the way, on these diagrams, time always runs on the y-axis. Go up, that's always time. So you think of this anti-de Sitter space, and you have a star in this anti-de Sitter space. That's this brown blob. The star collapses. It collapses to form a black hole. As you can see, it's becoming thinner. And then you can probe this geometry in the bulk with various bulk probes. And that's a standard kind of thing that physicists compute. And you can compute correlation functions in geometry using gravity. And these correlation functions give you some answer that you can calculate using gravity. And then you can ask the following question. Can you find some boundary degrees of freedom using whatever you like that give you the same correlation functions? Now, you might think that you have a lot of freedom because you can choose whatever boundary operators you like. But as Natty Seiberg was describing yesterday, in general, this is a highly overdetermined problem. And it's not always true that a problem of this kind has a solution. In fact, these modern versions of the information paradox can be phrased in the following language. It can be phrased by saying that you have some prediction for these correlation functions from gravity, and that there is no operator in boundary unitary theory, so that in some generic state of the black hole, the correlation functions of this operator are the same as what gravity predicted and side. That's a precise version of the information paradox. I want to point out to you that we have changed the language of the paradox a lot away from a contradiction between high-level calculations. One calculation in gravity that led to a contradiction with some principle of quantum mechanics, to something much more concrete, to a question of whether operators with certain properties exist in it or not. And that's something that's much more concrete that you can actually look into and try and understand. So I'll give you a very quick flavor of how these arguments are made. I'm happy to go into more questions. So basically, the argument is made by contradiction. So assume that some operator of this kind exists. If it exists, you can do an integral transform to extract the modes of this operator. And then gravity tells you, if you translate those correlation functions into properties of modes, gravity tells you that the modes have to have two properties. First, they have to have negative energy. The modes behind the horizon have to have negative energy. But yet they have to have the same occupancy as that of positive energy. And you can easily persuade yourself with a few simple manipulations that these two are in contradiction in some theory unitary. So I can explain, as I said, more in if questions about it. But of course, I'm going through this very fast, and so you could sit down and ask, what were the assumptions that I made in coming up with this contradiction? And if you think hard about it, you can come up with the following list of assumptions that one made coming up with contradiction. We made the assumption that the theory is unitary, which we'd like. We made the assumption that classical general relativity holds at the scale of the horizon, which we would like because we have black holes which are very big and much bigger. We made the assumption that the microcanonical and canonical ensemble are equivalent, which is a standard assumption in mechanics, which we like. We want the theory to be standard principle. Then we also made the assumption, if you think although it wasn't clear from what I said, that operators inside and outside the horizon commute exactly at space-like separation. And then we made the assumption that, in fact, if you asked for the answer to a local observation inside the horizon, The answer was given by an operator that did not depend on microstate of the theory. Now, these two you might think are very natural assumptions they would hold in any quantum field theory. But in fact, if you're willing to drop assumptions 4 and 5, these highlighted assumptions, then you can actually explicitly construct operators that have the desired correlation function. Then I'd like to turn this around and say that this is in fact telling us something about gravity. In particular, what this information paradox is telling you is that quantum gravity is unusual, very different from other local quantum field theories in the following two ways. First of all, it might happen that at times non-local effects in gravity are important. They may even be important over macroscopic distance scales. And second, it's telling us something even more unusual, that if you look at local degrees of freedom in gravity, operator that measures those degrees of freedom for you might have to depend on the state theory. So I'll spend the remaining 10 or 15 I have trying to describe these two phenomena. And I think they're two of the most come out discussions paradox. So let me start by describing this question of locality. So the proposal for this non-locality in some more detail is the following. As I said, you can black hole. Now there's this green cylinder here which indicates the horizon of the black hole, point of no return. And then you can think of points here, a point which is inside the horizon and some red points which are outside the horizon. Cross-sectional diagram on the right side. The proposal is that the degrees of freedom that live inside the black hole can actually be equated to some complicated polynomial of degrees of freedom that live outside the black hole. And if you think about this, this is a rather remarkable statement. Usually you think of degrees of freedom at one point in space from being very different from degrees of freedom at other points in space. Now this is actually a realization of an old idea called black hole complementarity, which goes all the way back to Soft, and then work by Susskind and collaborators, now almost 30 or more than 30. Now this is a remarkable question, and so you'd like more evidence for this. In fact, I'll describe how we have managed to gather some more evidence for this remarkable effect. At least some simple controlled settings, some systems where we understand a lot, we can actually get explicit realizations of this phenomena, and in some other settings we have some indirect evidence occurs. So the simplest setup in which you can examine this idea that there might be actually polynomial constraints between degrees of freedom at different points in space is empty anti-de Sitter space that doesn't have any black holes, is empty space. And then the claim is that you take empty anti-de Sitter space and you look at this ball, degrees of freedom point mark p, and you can rewrite them as complicated polynomials of degrees of freedom that live on this band very far away. And one thing I said time goes on the y-axis, is that this band is entirely space-like separate p. So in a quantum field theory, degrees of freedom that lived in this band b would be very different from degrees of freedom that lived at this point p, but the claim is that you can write down an explicit formula that relates the two of them. So I don't have time to go into the details of the formula, but I just want to point out that there is both a simple and an explicit formula that actually lets you write this degree of freedom here in terms of degrees of freedom somewhere else. Now this is a formula that in principle could have been written down immediately after AdS-CFT was discovered 20 years ago, but we just never thought to look for this effect till the information paradox told us that these interesting effects exist in black holes, and so we thought that maybe they should also exist in other places without black holes, and it does turn out that they turn out to be generic features of a theory of quantum gravity. In fact, let me make a heuristic argument. This is just a heuristic argument that non-locality is more generic. And the reason it's more generic is because all of you who've thought of the path integral formulation of quantum mechanics might have at some point wondered why is it that the world around us is local at all? Because the path integral instructs us to sum over all kinds of metrics, including metrics that are very different from the approximately flat metric that we live in. So how do we, why is it that we see an approximately flat metric? And the answer, of course, is that the world and the observations that we do are dominated by a particular saddle point of the path integral. And when we talk about locality in the world, we are talking about locality with respect to that saddle point. But the flip side of this is that it tells you that perturbation theory in quantum gravity is very important. Because if perturbation theory breaks down, then that's an indicator of the breakdown of the saddle point approximation. And that, in turn, tells you that your notions of locality might break down. So this heuristic argument tells you that locality in quantum gravity is tied to the saddle point approximation and to perturbation theory. and it motivates you to look for novel places where perturbation theory might break down. Let me describe some such settings where this happens. In particular, one such setting in which this happens is we claim that if you look at string perturbation theory, which is really just a fancy way of doing gravity perturbation theory, that this breaks down if you have if you try to scatter a large enough number of external particles, even if these particles have small enough energy. And the heuristic translation of this statement would be that locality breaks down if you probe space-time at too many points, even if these points are widely separated. Okay, so let me just try and give you some details of this because it makes relation to some of the other talks that we saw. So the basic point in proving this kind of breakdown of perturbation theory is to prove a certain bound on how fast string amplitudes grow. So particle physicists always like to talk in terms of scattering amplitudes. And where you scatter many particles together and you ask what's the amplitude, some other number of particles come out. And then there's some bounds you can prove, some general bounds on how fast these scattering amplitudes can grow within perturbation theory. And if they grow like n factorial for n particles, then it turns out that perturbation theory will eventually break down at some value of n. Okay, so how do we show that these scattering amplitudes in string theory grow like n factorial? In fact, you've heard many talks on this now. The basic idea is to reformulate string perturbation theory as some integral over the Weil-Peterson moduli space of some n-punctured sphere. And this Weil-Peterson moduli space came up in the talks by Ashok Sen and also by Mahan today. And then you make some arguments saying that there are many terms in calculating this amplitude, but the dominant term at large n is just the volume of this Weil-Peterson moduli space. And then we are lucky because the volumes of Weil-Peterson moduli spaces have been studied extensively in the mathematics literature. In particular, they were studied by Peter Zograf and Mariam Mirzakhani, who actually did a very detailed analysis of volumes of genus G surfaces with n punctures, and they have asymptotic formulas for how these volumes grow. We actually don't need all of these formulas. We just want to understand how volumes grow when the genus is 0, and that immediately gives us this n factorial growth that I mentioned, important for the breakdown of perturbation theory. So not all arguments rely on these fancy mathematical arguments. We can also just do a numerical analysis of string perturbation theory and verify this n factorial growth. But the bottom line is that string amplitudes grow very fast, and eventually, even if you keep the energy of all particles fixed, string perturbation theory breaks down, and this gives us a heuristic notion that locality breaks down if you probe space-time at points. Now, this is something that has many interesting effects. Here's one interesting effect. So many times, again, in this conference, the von Neumann entropy has come about. It came about in the previous talk, although I didn't have time to add the reference. But an important concept when you're in quantum field theory and many other settings is you have some degrees of freedom that live in some region A, and then you have the complement of A that lives elsewhere. And then you want to ask, what is the entanglement between A and A bar? So you trace out all the degrees of freedom in A bar, and you ask, what's the von Neumann entropy of this density matrix? But you can see that if non-local effects are important, then the Hilbert space doesn't factorize the way it would in some ordinary quantum field theory. And therefore, you need to think harder about how to define quantum information measures. This is something that we've been thinking about. We think this is something that's exciting new that can lead to many interesting developments about what happens in quantum gravity when the Hilbert space factorizes. Okay, let me come to the second physical effect that I mentioned was important. The second physical effect that I said was novel and came out of this thinking of the information paradox is what we call state dependence. This is actually an even crazier idea than the idea that you have non-locality, but we have some evidence which makes us believe that this is true. So the idea is the following. The statement is that you have some operators that do some measurements for you inside the horizon. You're asking some physical question about what happens inside the horizon. And you have some Hilbert space of the theory, which is given to you. But then the claim is that, in fact, you have to describe these operators patchwise on the Hilbert space of the theory. So really, if you think about this, this is, the first thing you learn in quantum mechanics is that operators are specified as linear operators in the full Hilbert space, and physical measurements are given by asking about, how these linear operators in the full Hilbert space behaves. But yet we're saying that if you want to ask some physical questions about what happens in the black hole interior, then you need to answer these physical questions with these kinds of operators that behave linearly only in regions of the Hilbert space. And then if you want to ask a question about some general state, you need to first pick which operator you're looking at, and only then can you answer happening. Now, why would this happen? So it turns out, and many people have looked into this, that once again the culprit is locality. So you see, the fundamental problem in gravity is that if you're asking questions about local physics, you first need a way of specifying where, what you mean by local physics. What do you mean by this point? If you're living in some fixed metric, then there's some way of explaining what you mean by some point here. But if the metric itself is fluctuating, then you want a way of saying that you want to look at the same point independent of what the metric fluctuations are doing. And one way to do this, at least semi-classically, is to use what people call a relational prescription. So what you say is you have some fixed boundary where the metric doesn't fluctuate, and then you set up some kind of physical process where you say you have an observer who jumps in from the boundary, this observer waits for a certain proper time, and then this observer makes a measurement. So you see that this specifies what the observer will do independent of what the metric in the bulk is doing. The metric might fluctuate, and then the observer might end up at some other point, but this is your definition of what it means to make a local measurement. Right? So you use this kind of relational prescription. Now the problem is that this is a semi-classical definition. Right? And what you really want is some operator in the full quantum theory that has the correct semi-classical behavior. Now, the problem which was recognized by many people, including I think most clearly by Daniel Jaffress earlier this year, is that semi-classical geometries correspond to coherent states in the full theory, and coherent states have a property, well-known property of being overcomplete. And if you therefore specify the behavior of some operator on all coherent states, then you're not guaranteed that that's something that will live to a good quantum operator, because you've over-specified the operator. So that's really at the root of what goes into the fact that these operators behind the horizon are state dependent. It's because if you try to specify them in some state independent way, then that leads you to over-specifying the operator, and therefore you need to specify them in these patches of Hilbert's. Okay. Now this is a very unusual claim, and it's also rather poorly understood, but I think it's something very exciting. It's telling us something very interesting about quantum gravity, and there are many questions that remain to be understood well. For example, one question is, what is the measurement theory of these state-dependent observables? So the standard measurement theory in quantum mechanics uses the von Neumann theory of measurement, where you take the operator that's going to be measured and you add it to the Hamiltonian, and that's clearly not a good prescription if you have these kinds of state-dependent variables, if these kinds of state-dependent operators. And then secondly, you would like to ask questions about whether there are any empirical effects of these state dependence, whether you would observe empirical violations of the Born rule. At least in some cases, you can argue that in black holes, in a standard set of experiments, you will not observe violations of the Born rule, but you would like some broader framework in which you can fit all of these things together. And it looks like you do need to develop this framework to completely understand gravity. Okay, so I'm done. Let me just give you a summary of what I said. The information paradox, as I said, is a very central problem in quantum gravity. It's really at one of the central obstacles that emerges if you try to put together quantum mechanics and gravity together in a single theory. Now, as I said, for a long time, the paradox was not very precise, and so you couldn't make much progress on it. But recent ideas allow us to make the paradox precise and frame it in settings where you can set up precise contradictions and do some set of calculations. And what these refined versions of the paradox reveal, as I said, were rather novel physical effects in gravity, and two of the effects I talked about in detail were the loss of locality and the state dependence of observables. And I think both of these are rather remarkable effects which really differentiate how quantum gravity behaves from quantum field theories. So let me say something about empirical tests. There are many scientists here who, one of the common questions you hear is about empirical tests. So these are extremely delicate effects, but when I was looking into this, at some point I happened to read Einstein's original paper on gravitational waves in 1916. And Einstein, did this calculation for gravitational waves, and then he computed the strain, and he found, this is actually an extract from the manuscript. If you look here, computed the strain, I don't know if you can see, he computed that the strain is for the 10 to the minus 27, and so he wrote in that paper, at least if Google Translate is correct, he said, in all conceivable cases, the strain must have a practically vanishing value. And of course, as we know, and as you'll hear much more today, this is not true. In fact, you could measure these very delicate effects, and they turn out to have very, very interesting implications. And so even very delicate effects, like the effects I'm talking about, can be measured, and they can be experimentally verified. Of course, the caveat being if you're given enough time. Okay, so I'll stop there. Thank you.
Thank you, Suvrat, for this very lucid talk. Physicists understand it, obviously, but I think computer scientists also got a gist of much of what was going on. Questions now?
So I'm not in this field, but from what I understood from your talk, you start with this AdS-CFT correspondence and you find that there is a contradiction of some sort. Gravity, the bulk and the boundary are not exactly corresponding. And from that you reach some conclusions about what gravity has to do, non-locality, etc. But the contradiction is a contradiction only if AdS-CFT is precisely valid. And am I correct in thinking that that is still a conjecture, or has it actually been proved for the cases that you are considering?
It depends, of course, on what you mean by proved. It's been checked in many cases, but I think you're right. Actually, that's an important question. You know, so AdS-CFT in many settings has been checked, and we believe it's true. It's of course not been proved at any level of mathematical precision. And it's certainly true that one of the things that some other people who work in this field would like to say is that this information paradox, so Polchinski, for example, would like to say that the information paradox tells you that AdS-CFT does not describe the interior of black holes at all. So I agree, and that's the reason I tried. So you're right that initially I reached those conclusions by saying that if you wanted to reconcile these things, you would need this non-locality and state dependence. But that's the reason I tried to give you some other independent evidence for why these kinds of non-local effects exist. So one setting in which I gave you this evidence was the case where you had no black holes in AdS. In that setting, we believe we understand AdS-CFT very well. And in that setting, you know, if we see these non-local effects, then we believe they're generic features of gravity. Similarly, I talked about this breakdown of string perturbation theory, which is really something that works in flat space, doesn't even require AdS-CFT. So it's true that initially we were led to think of these effects by trying to fit the interior of black holes within holography. But then we also have some additional evidence for these effects, which comes from additional arguments. So that's yeah.
A more elementary question. The assumption of equivalence of ensembles that you put in somewhat early in the talk applied to the field theory on the boundary or the gravity included theory in the bulk?
Yeah, it applied to the field theory on the boundary,
okay,
which we believe has standard statistics. You're talking about AdS. Is it relevant? It's a toy model of quantum gravity. You're probably referring to the fact that AdS involves a negative cosmological constant, which is the opposite of what's in our universe. But you know, AdS allows us to build toy models of quantum gravity. And the reason for that roughly is that AdS is a precise way of doing quantum gravity in a box. So if you want to understand general properties of quantum gravity, AdS-CFT is one setting where you can really understand quantum gravity and understand many questions about gravity. That being said, there were some things I said here which apply just to flat space, like this question of, you know, breakdown of string scattering amplitude for large numbers of particles is something that works just in flat space. So there are some lessons you learn from AdS, and then you try and see how far they can generalize to other settings. But it's true that AdS is not our world, but I think it still teaches us many interesting gravity. It's one setup where we can. Well, I wouldn't, you know, at least it's a toy model. It's one setup where we can understand quantum gravity. Quantum gravity is a hard problem, and this is one framework in which we can understand it. I don't think the fact that we're looking at a toy model means that it has nothing to do with nature. Many times when we have a hard problem, we look at simplified setups where we can understand it. And as I did say, the arguments, at least about, you know, the heuristic arguments about breakdown of perturbation theory implying loss of locality were things that would apply even in flat space. So in, you know, I think it's, yeah, that's what. I don't have more to say. But